Morning, everyone, or afternoon if you happen to be in the right states. Welcome to our Fire Behaviour Analysis Network webinar for April. This month, Miguel Cruz is going to talk to us about some work he and others have been doing around the Vesta model to update it and look at improving the, particularly the fuel inputs into the model. Most of you should know Miguel from CSIRO. He's been working with CSIRO for many years now on fire behaviour modelling and other fire behaviour research. So I'll hand over to him shortly. If you have any questions, please put them in the chat box, and we'll go through them at the end of the session. Thank you very much. Over to you, Miguel.
Good morning, everyone, and thanks for coming to this this seminar. I'm going to describe some work we have been doing last year and a half, funded by the New South Wales RFS, trying to come up with something, a model to predict rate of fire spread in eucalypt forests. And as Mike said, not just work by myself, Phil Cheney, Jim Gould, Andrew Sullivan, Lockie McCaw, and Musa Killing is just a few that contributed to this work. All right, so just for start, why this project, right? Kind of introducing why we are doing this, and for the F-bands out there, you probably know better than me that accurate predictions of fire spread are key, not just to develop a trust between the F-band and the rest of IMNT team, but also when there's critical fire scenarios to get timely warnings out there in devices. Having these accurate and rate of fire spread predictions are really key. In terms of the models that F-bands use in Australia, and talking here about the manual predictions, following the F-band curriculum, really we have 3 different models: Leaf of 80, MacArthur Mike 5, and Forest, and the Vesta. They kind of use throughout the full spectrum of burning conditions. But although there's some guidelines to where to use one model and the other, it's not really clear, and that also leads for some uncertainty in the model predictions. Going to, in particular, to the Vesta model, what we observed is that there's been a lack of uptake by the Vesta model since it has been developed. There's some reasons for that. One of them is this over-prediction bias for fires with slow and moderate or even high rates of spread, and that's why users tend to use the Mark 5 instead of Vesta for this kind of mid-range of fire propagation. Besides this over-prediction bias in that range, there's also other issues, namely that the model is quite sensitive to the fuel inputs, and these might also contribute to that over-prediction bias. That sensitivity to the fuel inputs and the subjective assessment of the visual fuel scores leads to quite a fair bit also of uncertainty in the model predictions. And that's just some of the feedback we've been getting from the end users throughout the last few years, justifying why people are not using more the Vesta model. Coupled with that as well is that the Vesta model was really developed for this kind of worst burning conditions where fuel moisture is homogeneously dry throughout all the profiles of fuels, and fuel availability is about 1, let's say, is full 100% full fuel availability. So the model doesn't take into account the effect of recent rainfall or changes within landscape dryness in the model predictions. So that's just a few of the reasons why, or that we took as the reason not the model to be more used overall. So we wanted to relook at the modeling, reanalyze the data, the experimental data, and also some of the other data sets that are available, try to improve the model to see if we can produce something that overcomes some of these limitations, right? So that's kind of the reason of this project. As we start the project, we had this stakeholder workshop where we met with end users from from most of the jurisdictions throughout Australia, and where end users told us some of the desired functions and attributes that the new model should have, right? And just going through a few of them in terms of spotting. Some people would like to have spotting effects decoupled from the rate of spread model, something that doesn't occur with Vesta or MacArthur right now. Build up periods of spot fires, information about the probability that spot fires are going to occur, density, distance of these spot fires, namely maximum spotting distance, and likely launch location. So just in terms of spotting, a few items here. Other desired functions in terms of fuel availability. People felt that we need to have a better grasp of the influence of weather on fuel availability, namely recent rainfall. How live fuel moisture content is tied also with fuel availability. Can we incorporate that in a model? Particular topic that was quite mentioned was the availability of wet forest to burn. Vesta developed for dry eucalypt forests. As you go to the wet forests, a different environment, how can you get a model that works also for the wet forests? And also fuel inputs should be linked to biophysical modeling or remote sensing instead of going through the visual assessment approach in terms of their assessment. There are a few more desired attributes, talking about thresholds of fire escalation, coalescence, how different fire or different spot fires, but also different fires interact between them, a function of distance and alignment with the wind. Identifying transitions in fire behavior that will allow us to better predict the burn windows to conduct back burns, for example. Also, after a period of inactivity throughout the overnight period, what are the conditions that are going to lead for a breakout of fire that already existed in the landscape? And as we build up in that spectrum of fire behavior, as the fire developed, issues about probability of crowning, under which conditions is this kind of behavior going to occur. Then also plume effects, fire-atmosphere interactions, build up of new fires, build up rate and time to steady state, ensemble of models, get error bars and uncertainty in the predictions. And after all these lists, that's when Mike Waters baptized this project, Vestopia, just because there was a lot to take, a lot of science that not even available to implement, that you first need to clarify before you can implement into a model to be used to decision support. And so starting with these ideas in the background, we went and looked at the data that we have available and think about how can we build a model that incorporates, if not all, most of these features. So I can develop a useful fire spread model. Normally, when you do a lot of this fire spread modeling, we have data available, we apply statistics, and you get a model, right? That is a model that is an image of the data that's being used, right? With this work, we felt we need to get something different. Then in the background, we have all these desired features. Some of them are not in the data available to explore through a statistical analysis. So we need to go circumvent this limitation and use some existing knowledge or evidence from other studies that are not really in form of data, but is knowledge that exists that we want to implement in the model. And this way kind of go around the limitations of the data and developed a model that suits the operational needs. So in terms of the data sets we had available for this analysis, for those that are around that have not, or like me, that start working in fire here in Australia after Project Vesta was completed. So these burns were conducted in WA about 20 years ago, or more than 20 years ago. There were 2 sites with 2 fuel types, one with a low shrub understory, another one with tall shrub understory. So the similar fuel types. They had 5 fuel ages to play with, so from about 2 years to about 22 years. You see that range over there, and that allows them to have quite a range of fuel structures, right? To cover the full spectrum, let's say, of fuel structure in dry sclerophyll forest, where you could conduct and have a sense of the effect of fuels on fire behavior. As experimental design, what they did, they conduct simultaneous fires. So 120 meters ignition for each one. You have a photo there on the top right of one of 4 of those fires. So we had same wind speed, same fuel moisture for all for a set of fires, but is really different in fire behavior, as you observe in the plumes in that image, are resultant from the effect of fuel on fire behavior, right? So then there are 10 replications, 5 light winds and 5 moderate winds. So up to the wind that was up to 25 kilometers an hour, but the fire really only got to about 20 kilometers an hour. And so, as you can see, in terms of wind speeds on the lower end, excuse me, of the wildfire propagation. In terms of fire behavior, intensity and rate of spread, these experimental fires, and it was a total of 116 experimental fires, are located on the bottom 10% of the fire intensity spectrum, right? So for our analysis, we need more than just experimental data. We also need to add some wildfire data sets to cover the full spectrum of fire behavior. And so for this project, we had 2 data sets available. One we use for model development. This is a data set that Phil Cheney gave in a 2012 paper, where he gave historical fires that occurred from 62 to 2009, and have the full fuel weather information for these fires. Of all the 31 wildfires he provided, we used 17 by remove some fires that had very small runs, or I'll get back to that later, very high drought factors. So we don't use drought factor right in early stage of development of the model, we use later. So in the end, we had 17 fires used in the analysis, modeling development. Rates of spread varied between 600 meters per hour to 9 kilometers per hour. Wind speeds up to 95 kilometers per hour. This for the Benham River wildfire in Victoria. And fuel age is from 3 years to long and burn, with fuel information coming from reports and case studies. So we relied this data set for model development, and because in the end we want to evaluate how the model performed, we left this other wildfire data set that was collated by Sarah Harris and Musa Killing, now in CFA, but back then in Monash University. And they collate and worked on reports, case studies, and also fire data from isochrones and weather data, and developed this wildfire data set with 183 wildfire runs. Of these, again, we used 90 of these wildfires by pruning some of the smaller runs or very steep runs, which would induce some uncertainty in the modeling analysis. Of these 90 runs, we had rates of spread vary between about 50 meters per hour to 80 kilometers per hour. Wind speeds up to 100 kilometers an hour. And this particular data set, fuel data, came from modeling fuel accumulation curves that took into account forest type and time since fire. For this data set, we had 71 wildfire runs with drought factor more than 9 and 19 with drought factor less than 9. And then later will be clear why you are separating these drought factor fires. So in terms of have to start looking at the data, what we have available, and looking at the literature, what kind of behaviors we are witnessing in some of the fires of interest. We kind of target some of the desired features that we want the new model to have, and you're going to be able to accomplish. In terms of effect of fuel structure variables, we went with easy to measure variables, and variables that are namely currently available and are easy to be modeled. So we're talking about fuel load, height of fuels, things like that. So we went away from the visual assessment protocols, given the body of work that's out there already that show the visual assessment do not really capture well some of these metrics, namely quantity of fuels in different layers. Another aspect we wanted in the model is the effect of the fuel variables is going to taper at high values. This meaning that, as example, if you think the difference between fuel load of 5 to 15 tons per hectare and 15 and 25 tons per hectare, you know that from 5 to 15, rates of spread increase much faster than from 15 to 25, just because fuel is not limiting, right? And you keep adding fuel, and it's less fuel that's going to be consumed in climate combustion. So we want something that has this effect of really, as fuel load increases to very high values, the effect of fuel load on rates of spread is going to decrease in terms of magnitude. Other aspect, this comes from some recent work, is that effect of fuel structure should vary with burning conditions. That's some of the also findings from the experiments in Vesta, and also early from Neil Burrows, that show that for very low intensity fires, fuel load was quite a significant variable, but as you start to have more intense fires, other features in the fuel complex, like namely the structure of near surface elevated fuels, start to have more of an effect. So we want to also include that in the model. Another aspect we wanted to include is this effect of wind speed, namely when you go into very high wind speeds and very low fuel moisture content. So here we really talk about the effect of wind speed in the severe and extreme catastrophic fire danger rating kind of range, right? And one analysis we did last year, we come up with this rule of thumb for wind speed, where for some conditions, wind speed alone explains quite well the propagation of fire. And this is really when wind speed is quite high, more than 30 kilometers an hour, and fuel moistures are quite low, less than 5% moisture content. So we're really talking about the high end of fire propagation. And for this high end of fire propagation, what we saw is that wind, and here we have a plot of the residuals here on the bottom left, residuals and observed rate of spread. Just using wind speed alone, you can see as the fires grow, spreading from 2 to about 10 kilometers per hour, wind speed prediction, a prediction of rate of spread with wind speed alone puts most of those fires within that 35 plus or minus error, right? So wind speed working quite well, explaining quite well rate of spread in the high end of fire propagation. What we saw also from this analysis, and this is just the evaluation of the rule of thumb just for the extreme end of fire conditions. In this red box, you see there is the residuals as a function of fine dead fuel moisture content. And what you see there is that after accounting for the effect of wind speed, moisture content has no relationship with the residuals, meaning moisture content is not explaining any of the residuals coming from a model with wind speed alone. So it seems that as the landscape, as the fuels become critically dry, lowering the moisture content is not really having an effect anymore. So moisture content is not a limiting factor anymore in terms of heat transfer that drives the fire forward. Another aspect that came from this analysis also looking at the residuals against understory fuel load and surface fuel load. So again, for these extreme conditions, with this data set, this data set from Victoria, from Southern Australia that Sarah Aris and Musa Killing put out. And for these extreme conditions, fuel load is not linked, does not further explain any of the error that comes from the use of the rule of thumb. So it seems again that for these burning conditions, fuel load is not affecting rates of spread, or just affecting really in a very marginal way, but not on the way we think fuel load affects on the bottom range of fire propagation. So this is just some of the things that are informing our modeling options. In terms of, go back to this fuel moisture effect, up to now, in most of our modeling fire propagation we have been doing, we tend to rely on this exponential decay function. And this just plot on the left is just a plot of the Barrow's fuel moisture effect function that's implemented in the Vesta model. And you have been using this Caton model for a while. But as you can see there, as the fuel moisture goes below 5, this kind of approach is saying that rates of spread are going to increase. And in this graph, you see the fuel moisture paired with the fuel moisture effect. And so it's going to, this kind of model is going to suggest a further increase in rates of spread with a decay of fuel moisture below this 5%, which we didn't observe in that wildfire analysis. Also, when you think at the other extreme of the moisture content range, when you go moisture content to 10 and 20, or sorry, to 20, 25 and above, you expect the fire to self-extinguish as the moisture content is above the fuel moisture of extinction. But when you apply this kind of exponential decay function for fuel moisture, you don't capture that behavior because the curve continues to suggest that fire propagation is going to occur even with very high fuel moisture contents. So from this, we try to model the effect of fuel moisture in different ways. And one, in this graph on the right, we have 3 curves. One is the same as the Barrow's function, that's what's there as a dashed line equation 3. But then we also tried a different approach. One of them was this linear equation. You see there where from one side it ends up about 24, 25. Fuel moisture effect is 0, so we have a multiplier that leads to a ceasing of spreading of the fire from a computational point of view. And as you go up in that curve, as it gets to about 5, there's a bit of a kink, and below 5 is just a fuel moisture effect of 1. So matching what the wildfire data was showing before. Another approach we also tried is this polynomial approach, which is more of a curve that we used to fit the Barrow's equation on the mid-range of fire propagation, namely between 20 and 10, and then goes to 0 of about 24, 25, and again goes to 1 as fuel moistures go below 5. Right? So that's how we try to capture some of that evidence, some of that evidence comes from wildfires, but were not in the experimental data set. Another aspect we are quite interested is implement some drought factor fuel availability function in the model that was not in the previous Western model. Now, this is a bit of a tricky, quite a tricky concept or issue. For once, we know with drought index, as in this figure from bushfires in Australia showed, a drought index goes up, a lot of the fuels on the understories, be it shrubs, perennial grasses, and coarse woody debris, moisture of these fuels goes down, right? All kind of, all in different ways, but all go down. And so drought factor tries to capture all these bulk effects, right? Not just one component, but all of them. And so, but it's a bit coarse, right? So the idea we had also was, okay, can we use different metrics? Can you use remote sense fuel moisture, live fuel moisture? Can you use soil moisture as a metric for fuel availability instead of drought factor, right? One thing it happens if you use live fuel moisture, you might not be taking into account the effect of that coarse woody debris, larger the fuels on the fire propagation, right? And so we're trying to kind of come up with something that integrate most of these things, but at the same time, we could apply in a modeling framework. So using data that is available for operational prediction of wildfires. We don't want to come with something that's too difficult to implement a landscape that then not allow its use, right? Also, another point here, in terms of drought factor, fuel availability, can you use different shapes, right? Instead of a linear shape, can you use something that better capture that effect of drought in fuel availability? And coming to the last of these desired features is these thresholds for escalation of fire and effect of spotting, right? And going back to this FBAN curriculum approach, where for a certain range of wind speeds or FFDIs, FBANs are going to use different models, right? Lift of 80 for bottom, then Mark 5, and then Vesta in the upper end. And really this approach really mimics this escalation of fire propagation as depicted in this graph on the right, come from work from Alan MacArthur. As the fire develops, it goes into different stages where early only ground fuels are being used or being consumed by the flame front. Then you have shrubs, the full understory, and then start in a dynamics where you start to involve the tree crowns and spotting behavior. So that's what you want to capture. And as you see for the differences on the models on the left-hand side graph, you kind of realize right away that probably one sole equation for, as we normally use empirical fire spread models, a sole equation will not capture all these dynamics, right? Because you see all these jumps. So you need to do something different in this respect. So we went to, what we thought about is to divide fire propagation into different phases. We tried with 2 phases, but then we come up with better results by assuming 3 phases. And the 3 phases we define is a phase 1, slow fire spread, rates of spread up to 2 meters per minute. A phase 2 is about moderate to high rates of spread, where fire spreads between that 2 meters per minute and about 25 meters per minute, or 1.5 kilometers per hour. And then a third phase, where fires are spreading with more than 1.5 kilometers per hour. So for this kind of analysis, we will need to partition our data set into the 3 phases and use the data within each phase to model rate of spread within each phase. And that's kind of the threshold or rate of spread we use for model fire spread in each phase. So for phase one, from about 10 meters per hour to about 120 meters per hour. Phase two, 100 meters per hour to about 2 kilometers, and so on. And you see that some superposition between the definition of the phases above and the data used in model fitting. That's just to kind of have a better conversion in the phases. Now, if you develop these phases, this model for rate of spread for each phases, we then need to link them. And to link them, we use this logistic regression analysis, where you're going to develop models that predict the likelihood of, or the probability that the phi spreading in each phase. In this case, phase two, likelihood that phi spread is more than 120 meters per hour, or probability that the phi spread at more than 1.5 kilometers per hour. They are in phase three. So in the end, we develop 5 models, and this figure here just shows the rate of spread models for the phase one, phase two, and phase three. Now, the models have different inputs, so they are responding to different environmental conditions, field conditions. And although here the 3 lines in this image, they go from 0 to 60 kilometers per hour, they are not to be representative of burning conditions within that range, right? So, in terms of the logistic regression models, the models determine the transition between phases. The likelihood that the phi spread in phase two is given by wind speed at 2 meters, so the understory wind speed, moisture content of the fine fuels, that's predicted by Stuart Matthews' that fuel moisture model, and the load of surface and near surface fuels. Then the model for the probability that the phi spreading in phase three, fast fires, is given solely by wind speed in the open 10-meter open wind speed and that fuel moisture content. So these are the logistic linkage models for the regression analysis. The rate of spread models, which for phase one is the model that gives rate of spread based on wind speed in the understory, moisture content, and again, fuel load. So we know that for slow spreading fires, it is really the fuel load on the surface fuel and near surface fuel. Rate of spread model also has the effect of the understory height. So in this state, you have an escalation of fuel of the fire within the understory, involvement of elevating and bark fuels and so on. And so understory height is really the main fuel driver of fire in this state, although fuel load still has an effect. And as you go to phase three, the analysis didn't find any fuel characteristic determining fire propagation. And fire propagation is really a function of wind speed at 10 meters and moisture content. So as you can see here, another need you have to run this model, you need to have a wind reduction factor that links the open wind with the understory wind. And up to here, we don't have yet the effect of drought factor and slope. So that will come later. Now, to use this model, the user do not need to calculate the rate of spread for each phase. Now, everything is kind of automatic. And what's done is that we have 2 or 3 rates of spread, and the overall rate of spread is a function, is a weighted average of the likelihood of this probability of the fire is in each function. So as an example here, on the left, we have a figure of the rate of spread curves as a function of wind speed for phase 1 and 2. And if you look for a wind speed of 10 kilometers per hour, we have for phase 1 about 100 meters per hour, and phase 2, 260 meters per hour rates of spread. Now, for this same 10 kilometers per hour, the probability that the fire is in phase 2 is 92%. So then on the right-hand side, we have the curve that integrates those two models with the probability model. And as example for that 10 km/h wind speed, we have the rate of spread is weighted by the likelihood. So we have 0.1 km/h from phase 1 times the 0.08 related to the 8%. That's remaining from the 92. And you have 0.26 km/h times 0.92, and then get the end result of the weighted rates of spread, right? So the model system is done in a way where this is just automatic, and in fact, it takes into account 3 phases. And this graph on the top just shows that over the full spectrum of wind speeds, let's say, you have the 3 curves of each phase, but then you have the integrated system with averaging of the rate of spread. In the bottom, we probably have phase 1 in the low wind speeds. Then you can see that most of the fire is spreading in phase 2 to about 20 km/h. And as wind speed increases, you see the curve going from phase 2 more into the phase 3, and wind speeds about 40 km/h. The fire is spreading at a phase 3 rate of spread, right? In the bottom here, this graph just shows some of the dynamics with this model, where we have, again, rates of spread as a function of wind speed, but 4 different fuel moisture conditions. 5, quite extreme conditions, 8%, and 11%, so much more marginal conditions. And you can see for the 5% fuel moisture, then quite early, the fire transitions into the phase 3, and you should expect. But for the more marginal conditions, it takes a lot more wind to take the fire into the higher state. And for the 11% within this graph, you don't see that occurring, right? So that's just shows some of that dynamics we attain with this model. Some more graphs showing that some of this behavior of the model, in this case, the effect of fuel load against surface and near surface on rates of fire spread. And this is just 2 graphs of the same thing, but on the left, we have lower wind speeds, just show better the effect. On the right, wind speed goes up to 50 km/h. On the lower range of wind speeds, what you see is that going from 10 to 15 tons per hectare, the difference is much higher than going from 15 to 20 tons per hectare. So again, that effect of fuel, that's going to be dependent on the fuel load. So it's not just a straight multiplication. Fuel effect depends where you are in the fuel load or fuel structure spectrum, let's say. If you go to the right-hand slide, right-hand graph, you see that the effect of fuel load, or the difference between the different curves, really becomes smaller and smaller as the conditions worsen in terms of fire spread potential. As you go for more than 30 and 40 km/h, that kind of difference between the different fuel load curves trying to be less and less significant. In terms of another example of model behavior, the effect of wind adjustment or wind reduction factor on the model outcomes. Here we have 3 curves. The yellow line on the top is a typical dry sclerophyll forest with a wind adjustment factor of 3. And as you see that if you go to different fuel types with a higher productivity, taller forest, more dense forest, well, we expect to have further reduction in the understory wind. So we have a higher wind adjustment factors. You start to see how the model responds to that. and starts to predict lower and lower rates of spread for the same burning conditions. And here on the right also there's a table that's based on data that published in different studies, and some work from University of Melbourne, Tom Duff and Kevin with a student, different fuel types, forest types, and try to link the effect of forest structure as cover and height in the wind reduction factors. We kind of link that with the model to cover the full range of stand structures in terms of impact of fire behavior. Now going to the landscape dryness, fuel availability, we try different approaches, consider different variables, but in the end we all have the constraint that if some of the most promising approaches were not going to be easily used in a field setting, because some of those inputs would not be easily quantified, right? And that was the case of trying to use something like surface and profile moisture content as used in the Red Book in WA to determine fuel availability. If the profile moisture content is not available at the landscape scale, we could not use an approach such as that. So we went for a more pragmatic solution, relying on the drought factor. And what he did, he tried two different approaches. One was using a linear function that links drought factor fuel availability as done by MacArthur, suggested by MacArthur work, and the other one was using a sigmoid curve that kind of more better mimics what we do with the curing effect in grass fire propagation. And we found out that this sigmoid provided better fit when you try to evaluate the model against the wildfire data. So indicating that this probably the sigmoid function is captured better what's happening in the field in terms of this link between drought factor and fuel availability. Now, what we did is also, because we did this modeling separate from the early modeling for dry summer conditions, this model approach allows us also to change the drought factor effect in fuel availability if we find something that works better. So this pragmatic solution can also think of it as an interim solution. If something better comes, we can also apply it in the system. In this graph on the bottom right, you see the impact also of using the sigmoid curve instead of a linear curve. If you have a linear curve, you'd have the effect of drought factor being quite well spaced, right? Would be a linear effect. With sigmoid, there's a higher effect of drought factor and fuel availability when you go for very low drought factors. And you see that the difference between the 4 and 7 is quite different in terms of fire propagation than the effect that goes from 7 to 10 drought factor in this bottom right graph. So again, just showing some of the behavior. Now we have the model. Let's try to look and try to show some of the evaluation results. Before I show some of the plots, I want to kind of show how we visualize the error in a plot form. So in this left-hand side, we have observed rate of spread of 1 kilometer per hour. You have a predicted rate of spread 1.5 kilometers. So we have essential error, which is 50% of the observation, right? And so if you plot that in that scatter plot on the right-hand side, that's where that kind of error would land. And what you do here, we like to put that we have a line of perfect agreement where we'd like all the data to be. And we have that envelope minus 35 and plus 35% error, where is an envelope where we data points that, and there we are quite happy with those simulations. Like it's about how we tolerate error, let's say, in these fire behavior predictions. So showing, going forward and trying to show some of the graphs and statistics we got, essentially I use two statistics here. This MAE, the mean absolute error, is error in an absolute form, so there's no plus or minus, and also this MAPE, that's the error as a percent. And these two graphs, we have the model fit against the data used in its development. On the left, we have the experimental fire data, and on the right, you have the wildfire data. You'll notice that in terms of range, on the right, experimental fire data goes to about 1.2 kilometers per hour. Wildfire data, tenfold increase, goes to about 12 kilometers per hour, right? And so when you go, you look into these error metrics, you look into these both, you need to look into not just absolute error, but also the percent error. As an example, we have about 110 meters per hour for the experimental data set in terms of mean absolute error, and that is a 46% error as average. It's quite a normal result when you are evaluating models against the model, the data used in model development. But when you go to wildfire data, so the error, mean absolute error is again a tenfold increase as well, is 1.15 kilometers per hour. Just has to do with the range of the data we are using, of the observations. But in fact, as a percent, the error is lower for the wildfire than it was for the experimental fire data. So the MAPE for the wildfire was 35%. And most of the wildfire predicted within that plus or minus 35%, with a few cases that are some few fires that lower spreading fires with more notable under predictions. Going to evaluation against some of the more independent data sets, that's where the models really start to show if it works or not. Here's some data from Project Aquarius, that's from the 1980s, some experimental fire data in WA. Again, similar range to Vesta, 0 to 1 kilometer per hour. And in terms of model fit, most of the data within that plus or minus 35% error, average error 0.13 kilometers per hour, and a MAPE quite good, below 40%. So again, a good outcome for the model in this respect. Again, in this situation, we know very accurately the wind speeds, the fuel conditions, and the fuel moistures. So all these variables were measured on site, and so with precision. So the data, the model predicts well also because of that. Now, when you go to a wildfire situation or try to evaluate the model against wildfires, you are likely to have much more spread uncertainty in the input conditions, and you can expect to have also more uncertainty in the outputs of the model. So this slide shows the evaluation against that Sarah and Musa wildfire data sets. In this case, we do separate the evaluation of the model between drier conditions with drought factors more than 9 and not so dry conditions with drought factors less than 9. And so for dry conditions, what you see, mean absolute error, very similar to what was observed before, 1.26 kilometers per hour, and as a percent is about 83%, right? So much larger than what you observed before. For the drought factor less than 9, very similar statistics, mean absolute error 1.16 kilometers per hour, and MAPE about 90%. So very similar to the dry conditions, which kind of justifies the drought factor fuel availability modeling that we went through. Now, 2 points to consider in these numbers as well is that these are really these simulations of the model against wildfire data are what we call a blind run. So just using the weather data from a nearby weather station, you have assumption on fuels and assumption of fuel moisture and so on, right? As F-band doing fire simulations, if F-band is using is smarts, is adapting or is fine-tuning the weather forecast for the local conditions. He knows more about the fuels than what we know about the fire that happened 30 years ago, and so on, and knows about what the fire had been doing the previous days. The F-band will likely obtain errors much lower than these ones, right? That's where the F-band role comes as a user of models that incorporates not just the model, but all the know-how that comes from the experience. Another very interesting aspect in this graph is that when you look to the plots on the right, namely the top one, you see that the average residual as a function of observed rates of fire spread. So that's, in this case, we put the rates of fire spread within classes less than 5, less than 0.5, 0.5 to 2, 2 to 4, and so on, kilometers per hour. On the top graph, you see that early there's some over prediction, not too bad, and then there's some under prediction, right? But close to the zero line, really. When you go to the bottom, the percent error graph, what you see is that the slow spreading fires are really the ones that have larger errors. As the rate of spread increases in the observed rate of spread, what you observe is that there's a decrease in the percent error. And as you go to the 2 to 4, 4 to 6, and 6 to 8, this error from the model is lower than 25%, right? Plus or minus 25%. And this also has to do with fire simulations for conditions of lower wind speeds, low spread potential. There's a lot more uncertainty on the wind speeds that are driving the fire. Whereas when you go into conditions where we have stronger winds, it's more likely that strong winds are homogeneous within the landscape. And so there's less uncertainty in that drive of fire propagation, and then you end up having better predictions from the model. Right. So in this case, quite happy that the errors for the high end of fire propagation, when you really need to use the models in more critical situations, the model is predicting quite well in terms of percent error. Going to a few last slides. One is about spotting. How about spotting? How is that incorporated in the fire propagation in the model? So is implicit in these models, spotting is implicit in the models, because spotting occurred in wildfire data set and also some that experimental, high-intensity experimental fires, right? The effect of spotting is not really clear in terms of fire propagation. When is it spot fire really going to lead to a substantial increase of rate of spread relative to what the model predicts is not clear. And that's a good example here, this image from a paper from Michael Story, University of Wollongong, where you see quite a large fire, quite a number of spot fires ahead of it, most of them landing in that wake zone ahead of the fire. And you don't see those spot fires spreading with a shape that you would see in the new fire, right? The nice elliptical shape going with the wind. A lot of the spot fires in that image they seem to be blobs within the landscape, just because they are in that wake zone and not free from the influence of the main fire. So this is what we believe is occurring in the data from that we use in our work. It's also the case where spot fires are land at such distances that overcome this kind of effect of the wake zone, right? So spot fires more than 10, 15 kilometers. And that's likely that those spot fires are likely to lead to some under prediction relative to what the model overall, in terms of overall fire propagation, there'll be under prediction relative to what the model indicates. And we found that in a couple of case studies where there was talked about authenticated 10, 15 kilometer spot fires. And we found the models to go into that under prediction trend, not too much, but a bit of an under prediction. Just summary, model inputs. So 10-meter open wind speed, as previous models used from forecasted or combination of forecast observed weather. Not much of an issue, not much of departure from use of previous models. We need to know the wind reduction or adjustment factors as a function of fuel type. A lot of jurisdictions already have that information that they use in softwares like Phoenix and for manual predictions as well. A lot of that guideline already exists. And that fuel moisture content, we are using the moisture content from Stuart Matthews. Important to use that model because that model is consistent with the fuel moistures that were used for predicting moisture on the wildfire data set, where there was no measured fuel moisture values. So this model system should rely on moisture content estimated by this model. Fuel load of surface and near surface fuels can come from fuel accumulation curves, maps, or some more biophysical modeling that can occur in the future. Height of understory fuel layers. So this is the average of near surface and elevated fuel layers. Not sure, some jurisdictions already have the information that already was used for applying VESTA, namely near surface fuel height for the rate of spread of VESTA and elevated fuel height that was used for flame height calculations with VESTA. So some of this information already exists or needs to be determined or approximated from knowledge of fuel types and things like that. Drought factor, what you're using right now is from latest rainfall, time since rain and drought index. And then slope, I didn't talk much about slope, but what we prescribe is continue to use what's used in Australia, MacArthur rule of thumb that was parameterized by Noble through that exponential function. So there's still room for improvements in this work. Some of the errors we identified to be early morning fire runs is something that when you compare with the wildfire data sets, and we suspect that we are not capturing well some of that overnight moisture recovery and the remnants of that moisture affecting fire propagation early morning or late morning and also early afternoon. So found that it might be better if you could also capture some of that overnight fuel moisture recovery effect. Looking forward to also better incorporate fuel availability to different metrics. So again, a lot of people working on this respect, and they might be able to come with a better metric than drought factor. Phase 1 spread thresholds, I didn't talk about that, but talk about the go, no go. So from no fire spread to fire spread. That's something that we don't have models. There's some work being done also by the University of Melbourne for wet forests, linking fuel moisture and likelihood of propagation. But it's more in wet forests, but that's something that also needs to be extended to dry forests. And also to finalize, we also need a better understanding of spotting influence on fire propagation. A lot of good work coming last few years, looking at the line scan data. But we need to further extend that knowledge, probably to better understand when spotting going to lead to effects different than what we have included in the model. And that's all I have today. 1 hour and 10 minutes. Thanks very much for all that lasted all this time. Mike, I pass it to you, and yeah, any questions would be.
Thanks, Miguel. There's a huge amount of information in there. It's almost too much to digest. I've got one question. So in phase 3, if fuel load is not a significant factor, how does this then relate to the likelihood of likely effectiveness of fuel reduction under those phase 3 fires?
Yeah, that's.
I think it sort of answers itself, but
the question. I have a lot of discussions with Phil Cheney, Lucky, and Jim about that. It is a fact because the way the model is set up, the likelihood, if you have a prescribed burn, the likelihood that a fire will get into even phase 2 is not going to be there. So if you have very incipient fuels, the fire is not going to get into phase 2. So then we will not get into phase 3 as well, right? So that's how that is incorporated into the model. So although the rate of spread model for phase 3 do not take into account the fuels, the fuel effect is incorporated into that linkage functions. And if linkage functions limit the transition, you'll never get phase 3.
Thanks, Miguel. Brian has said, thanks for the spotting section. That was really good. He just asked, what's your confidence in that research so far? And is more required, which probably is a rhetorical question.
Yes, no, it's very interesting, results. In fact, some things got. All right, we know spotting. Spotting is key to bridge gaps in the landscape, getting fuel, right? We know that. Be it also gaps in fuel or breaks in topography that will slow down fires considerably. And through spotting, the areas of low fire spread potential are overcome by wildfires. So that's one effect of spotting. The other one is the effect of spotting as you have continuous fuels, let's say, an interrupted potential for fire to spread. And that's where it's unclear. And it's very difficult to decouple because fire is fire. Fire doesn't decouple things. And you decouple what the flame front, just like radiative heat transfer, convective heat transfer propagation, and spot fires, right? You cannot take that apart. And so what you see, really, what the wildfire shows is already those things together. And one thing that shows that, as example, Michael's story results, one of the things that came up from his analysis that spotting distance maximum spotting distance increases 3% of the wind speed, right? As you increase wind speed, so the likelihood or the maximum spotting distance is going to increase as 3%. But we have results from this rule of thumb that shows that as wind speeds increase above the 30-kilometer threshold, rate of spread increases 10% of the wind speed. So that suggested that those spot fires are going to be overcome by this process of fire spread that includes, again, those convective, radiative, and spotting distance. So again, it's very difficult to decouple. I'm not sure if I'm answering the question. I don't think I am. But yeah, further work is necessary. And the way that work has been done, I think that's the way to go, really. Line scan data is our best chance to capture some of that spot fire dynamics.
Thanks, Miguel. There's a question from Tom that's suggesting the model looks really good. Have you thought about whether the model could be extended into heathland and mallee fuels where the elevated fuels are treated similarly, I suspect, in your previous work?
So the model or the model, I'm not sure if it's the modeling or the model framework. No, I haven't thought about that. I haven't thought about going into that, how to go from here into the mallee. No, I haven't thought much about that.
I suspect a relevant one is there's obviously a continuum between heathy forest and heathy woodland, and which model has been, where the model kicks in. But if you've got the framework the same, it sounds like there's you can adjust. We can just find the factors and adjust that down the track with more case studies.
Yeah, and it might be the case where, so with some of that heathland or mallee, obviously we have that gaps in fuels that limit fire propagation. But as the fires start to spread, again, it might be something that things just come together. If you take into account with the right wind adjustment factors and right fuel structure described, it might be that things really fit into each other. But yeah, something that needs to be looked at separately.
Thanks. Brett's come back from his first comment about the fuel reduced areas, saying if a phase 3 fire hits a fuel reduced area, will it continue as a phase 3 fire?
Yeah, so that's a good question. I guess when you think about spatially, all right, so a fuel 3 phase fire, a phase 3 fire is probably going to throw a lot of spot fires. So depending on the size of these fuel treated area and the size of the fire might just go around, or might be stopped by this treated area. Again, it goes back to how do you treat spotting on a spatial framework, right? It's tricky because because you cannot decouple spotting from the fire propagation. When you go to a spatial modeling framework like Phoenix or Spark, you need to treat spot fires in different ways. So spot fires need to be there to bridge areas of discontinuity, but at the same time, you need to be careful not to double count the effect of spotting. It's already in the model, right? So that is up to the modeling. We need to figure out ways to do that accurately, really. So again, go back to the answer. If the spotting distance is lower, or the treated area is smaller than the spotting distance, the spot fire is going to overcome this area. So the area needs to be big for that. And again, could go back to things like that rule of thumb that results from Michael's story, with the maximum spotting distance being 3% of the wind speed, and kind of gave an idea what area will breach, what kind of, under certain conditions, is the spot fire going to breach this fuel treated area or not.
Does the non-parabolic shape of the small spot fires support the finding of higher rate of spread uncertainty at low speeds? What do you think it's different?
Or is different in that is different in the sense that those spot fires really were in the wake zone of the plume. So they're being affected by that large energy source that's blocking the wind. Within a landscape where we have low wind speed, let's say average wind speed is about 20 km an hour in the region, in the area, there'll be areas with much more wind, different directions than others. So it's not really the same, the same, because it's about having a fire in landscape affecting the downwind environment, or having no fire, or having using no fire but having variable winds on the landscape.
Almost there. Sean says, great talk. Have you looked at the possibility of the role understory plant species plays in terms of having different leaf traits, different flammabilities, leading to different properties of litter? Or is that?
No, we didn't look into that. Our experience, and goes back to these results from the rule of thumb evaluation and so on. Fire will be very sensitive to small scale changes in fuel structure in the bottom range, right? In that case, again, could be, if you talk about that phase one, talk about you put a log on the ground and the fire will not cross the log, right? You have different species, and it might structurally affect fire behavior. Now, as you go to phase two and phase three, the combustion wave that drives fire propagation is gas, superheated. It does not see those, it doesn't really care much about those changes anymore, and just kind of go, just flows around things. What is available is ignited, what's not available is going to be ignited later. But that combustion interface that drives fire propagation, that really just feeds on what's most efficient ignition in heat transfer. So a lot of times, again, we don't need to have many fuels that lead to very efficient heat transfer. If you have just a few of them, that's allowed to carry the fire, and other things burn later within the flame, let's say. So we haven't looked much into that. Even aspects like we talk about fresh litter, old litter, fresh litter, even for the same species, fresh litter will tend to have more chemicals, and structurally is more fluffy than the old litter, right? But we are not able to look into that, to incorporate those things in this kind of modeling we do. So yeah, we're not looking to that. We are looking more of the bulk effect, bulk conditions, let's say.
And last question from Simeon. Do you think the fuel parameters you chose are constrained by what was collected historically? For example, if we describe the fuel better with new technology, would that help at phase one where there appears to be higher errors?
Yes. So it's not constrained like fuel loads. We can do better with fuel loads. For sure, and you can do better about that height of the understory with LiDAR and things like that. There's a lot of promising methodologies out there being used right now that could provide better inputs for sure. So I think this approach we used was kind of pragmatic as well. We can use with what we have, but we can get better, and by that better, reducing some of those uncertainties in the fuel mapping and characterization, and with that get better simulation outputs. So
Oh, look, thanks, Miguel. That's really, there's a lot packed in there and a lot there. Do you have a time in mind, a timeline for when you think the model might be available for us to put for people to use? Obviously, it needs to be published and packaged in a way we can use it.
yeah, we are. So we are about to, for of this component of the study, deliver, submit a paper and deliver a first report, and we're still working on other aspects like the fuel estimation and also spotting the dynamics, but they don't constrain the use of the model. So, but yeah, so we are close to submit this work to be published, and then it's up to the agencies when start looking how it feels and how they can run with their existing data sets, essentially.
No problems. Thank you very much, Miguel. That'll certainly give us something to think about for the next few weeks and months. Yeah, thank you very much. It was great.
Thanks, Mike. Thanks for the invitation and the opportunity to present this work. And yeah, hope to continue this dialogue.
Now, thanks to Greg for the tech support. Thank you all for joining. If you have ideas about what else you'd like to see presented in these forums, by all means send myself an email, and we'll talk to you again soon. Thank you very much.